Welcome to the Explainer. Today, we're digging into a force you use every single day, even if you don't realize it. Magnetism. Yeah, it's what holds stuff to your fridge, sure, but it also guides our compasses and pretty much powers our entire world. But here's the thing, it's governed by some really strange rules. So let's just jump right in with a question you've probably wondered about if you've ever played with magnets. Get this, you snap a magnet in two, right? You don't get one piece that's all north and another piece that's all south. Nope. Instead, you get two brand new, smaller magnets, and each one has its own north and south pole. Why on earth does that happen? Well, the answer reveals something truly fundamental about how our universe is put together.
All right, so to crack this mystery, we first need to make sure we're on the same page. Let's quickly go over the basic rules of the game, the things we can all see for ourselves just by messing around with magnets.
You already know this stuff from experience, right? You try to push two north poles together and it feels like they're actively fighting you. Or you let a magnet dangle from a string and it lines itself up with the Earth's own massive magnetic field. And of course we know that some materials, like a simple iron nail, can be turned into magnets. These are the basic, observable facts.
But here's the kicker, the one rule that's a real head-scratcher. This partnership between north and south is absolutely unbreakable. Think about electricity for a second. You can have a positive charge, like a proton, just hanging out all by itself, no problem. But with magnets, no way. You will never, ever find a north pole without a south pole attached at the hip. This is the whole no magnetic monopoles rule, and it's the very puzzle we're going to solve today.
So our first clue to solving this whole thing? Well, it lies in being able to see something that's normally invisible. We need a way to map out the hidden architecture of magnetism. Okay, this is one of my favorite classic experiments. It's just so cool. It's like being a detective, you know? You sprinkle these little iron filings around a magnet, and suddenly, bam, you see the fingerprints of this invisible force. The filings are literally forced to line up along these invisible pathways, giving us a perfect map. And what we're looking at here, these patterns are called magnetic field lines. You can think of them as invisible highways for the magnetic force. They show us which way the force is pointing and how strong it is, and they have some very specific rules that are totally key to our mystery.
Now, pay attention to this part, because it's the giant clue we've been looking for. See how the lines flow out of the North Pole, arc around, and then go back into the South Pole? Well, here's the wild part. They continue right through the magnet itself to form a complete unbroken loop. They are always continuous, closed loops. That's a huge hint.
And this right here is a massive revelation. The magnetic field from your average bar magnet looks pretty much identical to the field you get from a coil of wire with electricity zipping through it, what's called a solenoid. This tells us something profound. Magnetism doesn't come from some magical property of northness or southness. The bottom line, magnetism comes from moving electric charges, period. Okay, so we've got all the pieces. Let's put them together for the big reveal. The fact that these magnetic field lines are always loops isn't just some quirky little feature, it's a fundamental law of the universe. This is where you can really see the huge difference between electricity and magnetism. Electric field lines are kind of like one-way streets. They can start on a positive charge and end on a negative one. But magnetic field lines? They're like circular racetracks. They have no beginning and no end.
So this whole racetrack idea, well, it's actually a fundamental law of physics. It's called Gauss's law for magnetism. And in simple terms, what it basically says is this. If you draw any kind of imaginary box or bubble anywhere in space, the number of field lines going in has to be the exact same as the number of lines coming out. Always, no exceptions.
And there it is. That's the aha moment. Because those lines have to make a complete loop. You just can't have a starting point, like a lonely North Pole, without it also being connected to an ending point. Every line that leaves has to come back. So when you cut that magnet in half, you're not splitting the poles. You're just giving those loops a new door to come in and out of. And just like that, mystery solved.
Okay, so now we know why magnets always have two poles. It's all about those loops. But what happens when you introduce this invisible force to different kinds of materials? As it turns out, not everything reacts in the same way.
Believe it or not, pretty much every material in the universe responds to a magnetic field somehow. We can basically sort them into three main categories based on how they react. And as you can see here, their behavior ranges from being ever so slightly pushed away to being powerfully pulled in.
Yeah, let's give them personalities. It makes it way easier to remember. First up, you've got your diamagnetic materials, like water or copper. Think of them as the introverts of the material world. They actually push the magnetic field away, just a tiny bit.
Then there are the paramagnetics, like aluminum. They're like casual friends. They're weakly attracted, but they're not going to go crazy over it. And finally, you have the ferromagnetics, like iron. These are the superfans. They are strongly attracted and can even become permanent magnets themselves.
So what's the deal with stuff like iron? Why is it such a superfan? Well, the secret is all about teamwork on a microscopic scale. These materials are made up of tiny little magnetic regions called domains.
Okay, picture a totally disorganized crowd of people, all pointing in random directions. That's basically a normal piece of iron at the microscopic level. You've got all these tiny domains, which are like mini magnets, but they're all oriented randomly, so their effects just cancel each other out, and the whole piece of iron isn't magnetic.
But then you bring a strong magnet nearby, and it's like a drill sergeant shows up and yells, "Attention!" All those little domains snap into line, all pointing in the same direction. Suddenly, they're all working together as a team, and their combined force creates that powerful magnetic attraction we're all familiar with.
All right, let's just zoom out one last time and really appreciate how fundamental this whole thing is. This force is, well, it's literally everywhere.
If there's one single thing you take away from all this, it should be this. All magnetism, all of it, from a tiny fridge magnet to the enormous magnetic field protecting our planet, comes from one simple source: electric charges in motion. That's it.
And that one simple idea has some seriously huge consequences. I mean, this quote just says it all, doesn't it? This isn't just a force for our gadgets. It's woven into the very fabric of the cosmos, from the tiniest atoms to the biggest galaxies.
So that kind of leaves us with a final, pretty mind-bending thought, doesn't it? We're literally swimming in an ocean of these invisible forces. Our technology depends on them, our planet is protected by them, and they're generated by the very atoms we're made of. And it really makes you wonder, right? What other unseen magnetic fields are out there shaping our world, shaping our technology, maybe even shaping us, just waiting to be understood?